If that works. Okay. All right. So today we're going to do. Should be the pretty fun one, I think. So a lot of what we're going to talk about for today, there's some practical stuff toward the end, but it's really kind of theoretical. What I want to do is, this is sort of analogous to when we talked about maximum likelihood, which is, I know, everyone's favorite day. But I want to sort of try to demystify this. There's nothing really magical about what's happening here. And so with some really simple examples, we can actually see what's going on when you do Pgls, which is, so much in the same way that you can actually see sort of what, least squares regression is doing, or, what it is to calculate a likelihood for something, right? We can essentially do the same thing here. And you're not going to, in practice, do any of this manually, right? That's crazy. But it's important to know what it's doing, right? It's like we need to know what our functions are doing. And it turns out that it's not really that complicated, right? And we can basically build it up from least squares regression and then just basically stick a phylogeny in there. And that accomplishes the exact same thing. So that's the plan. So we'll see how it goes. So I think the none chapter hopefully was a good review of independent contrasts. They still are the simplest way to go. I don't use them very much because, for all the reasons why Pgls is more useful than independent contrasts. But if you've got the data and the question that it works for, then it works perfectly well. And they're not just numerically equal methods; they are equivalent. They're numerically the same thing. Go back to that later. This is a really good book. It's a lot about how to do this stuff, specifically in R. So Emmanuel Paradis wrote and maintains the ape package that we use a lot. So he's got, this is the second edition. There was a first edition that was about 6 or 7 years before this. So this is really good. There's a lot of other good stuff on there, a lot of things like links I gave you in the previous lectures. All right, so this was this was actually just the slides that we did at the end of last Friday. So we can simulate some data, make a tree, simulate data under 2 different models. We're actually going to do this in reverse later on. Not so much today, but more, actually, yeah, a little bit today, but more explicitly on Friday. Simulate data under 2 different known models, right? So we can simulate data with a Brownian motion model and under an OU model. So a Brownian motion plus kind of a selective, toward a selective optimum. And here I put the optimum at 0, so it doesn't really move. And it should hopefully be clearer, maybe not clear, but getting clearer about what these should look like, right? So we should get some spread with Brownian motion, and we should get less spread with OU, right? That it basically constrains that, right? And we could essentially we could change this, in Brownian motion, we could change this variance parameter, and we could get this same pattern, actually, right? We could get this, right? That would do the same thing. Does that make sense? Why? That variance, this little piece right here, sigma squared, that's just how big of a step you can take each time. And so we can, if we make small steps, we can get a pretty narrow range of drift, right? So those mimic each other, right? And so that's actually kind of an interesting point, because it means that in some cases you actually can't tell the difference between OU and Brownian motion with a very, very small step parameter, right? So effectively you could get the same pattern, right? And they would be indistinguishable from each other.
That's only if they if the optimum is, it's stabilizing selection.
Right, again, if it's stabilizing selection, if it's already at the optimum, you're right. But if it was, so if the optimum was actually up here, you'd see it wander its way up there. Okay. And then we can fit different evolutionary models. We'll come back and do more of this Friday. And if we fit, the data we know to have been produced by Brownian motion, and then we can fit 2 different kinds of models, and we see that the Brownian motion data fit to a Brownian motion model fits better. It's got a lower AICC than if we try to fit it into an OU model. And the opposite is true for the data that's simulated by OU. And we can actually do this in reverse, where we don't know the model, and we can actually say which is the best model, right? Is it OU, or is it Brownian motion, or some other model? And we'll do a little bit of that at the end today, and we'll do it more on Friday. And this is just standard, AICC comparisons, so nothing new or unusual here. All right, so that was last week. So we did the history of independent contrasts on Friday. They're proposed in the mid-'80s, and by the late '80s and early '90s, there were actually programs that could do this. And so most of you were either not born or were only very recently born then. So you do not remember these dark days of computers. It was dark indeed. Yeah, this is like, I don't know, it was 85. That was like the first quote unquote portable computers were like 85, 86, 87. They were portable. They were like this big.
Lunchbox.
Yeah, bigger than a lunchbox though. It looked like a small suitcase. Like I'd beg my dad to bring it home, and it had a screen like this big, and it had 10 megabytes of hard disk space on it.
Our program kept there, so Dennis, it was in his office, so
Yeah.
giant.
So, and so shortly thereafter, Alan Graffin wrote this very, very, very long paper called The Phylogenetic Regression. It basically said, this should work. And it's this it's like really long and impossible to read. It was like essentially all math. Basically said we should be able to do this, right? We should be able to, rather than calculate independent contrasts, we should be able to essentially put the tree in as some sort of a weighting scheme, right? That we should be able to sort of weight the shared distances among the shared evolutionary history among the tips as a way to sort of scale or kind of transform the observations. There are a lot of proofs and a lot of stuff in there. He did write a program, it's called GLIM. Never really got much use. This is actually from the paper. 56 species and 42 nodes, took only 7 seconds of CPU time on a VAX 8700. So anybody know what a VAX 8700 looks like? It's like half of a fridge. Finally got around to about 25 years later actually writing an R package for this. So there was the PhyReg package. It was actually on CRAN as of February 2014. So that took 25 years to happen. I actually downloaded, I found the GLIM program. It's essentially, you can't even read it. It's like machine, it's not quite machine language, but it's pretty close to it. Okay, so however, it was known pretty quickly that people got very, very similar results, like to the number of, to however many decimal places you could calculate. The slope you would get from an independent contrast regression through the origin was asymptotically, or it seemed at least to be very, very similar to what you would get from Pgls, right? To as many decimal places as you calculate. That doesn't mean that they're actually equal. It means that, as far as we can tell, they're equal. And so this was an ongoing question for a very long time. Until 2012, the proof finally was proven. So now we're very certain that they're actually numerically equivalent, right? It's like saying 1 equals 1, right? Now we know that they actually are exactly the same. And this is, again, only for Brownian motion model of evolution. And so that's, again, independent contrasts assume a Brownian motion model. Okay, so there we are. Now we know that PGLS and independent contrast are they're not just doing the same thing, they are the same thing. So they're really two sides of the same coin. And so there are ways with independent contrasts, once you get the slope, that you can go back and figure out what that intercept should be, even though you've run it through the origin. You can basically back calculate what that should be. And the numbers always came out the same to however many decimal places, but now we know that they actually are the same. You can read this Blomberg if you really want to follow it. I'm okay just saying that they're the same. All right, so why would we do PGLS instead of just independent contrast? So there are a few really big improvements here. The first, and I think for me the biggest one, is that you can deal with any number of continuous and categorical variables, right? So any sort of a linear model that you could imagine, right? So an ANOVA, one-way ANOVA, two-way ANOVA, an ANCOVA, parallel slopes, different slopes, anything you can imagine as a linear model you can do with PGLS. And you can do other kinds of models, right? So that actually you can do generalized linear models, right? So you can do logistic regression. There's logistic phylogenetic regression. You could do, any sort of a distribution of an outcome variable that you can imagine, you can do it now. That is a lot harder to do. It's not impossible, but it's a lot harder to do with independent contrasts. Right? So we pointed out the problem of, if you want to calculate contrast for some sort of an ANOVA model, right, and you can assign all of the nodes, all the contrast to one group or the other except the root node, right? You don't know which one because that's any node where the categorization splits, right? You can't assign that to a group. That's a big problem. It's not a problem at all with PGLS, and so we'll do at the end of today. I'll show you how we would do that home range area body mass, right? The old 49 LBR data, right? We can fit it really easily in PGLS. It would require some contortions to do with independent contrast. You could do it, but it would take multiple steps, right? You probably first have to standardize by body size, pull out the regression, pull out the residuals, and then use the residuals, and then categorize the residuals, and then figure out how to deal with the root node. But you could do it, and it has been done. But we can just circumvent that. We just don't need to do it anymore. The other big one is that we can allow different models of trait evolution, and we can actually compare them, right? So we can do our model comparison with not just what kind of model is it is an OLS better, or is it constrained slopes, or is it different slopes? But now we can say all of those things with different evolutionary models. So we can the example we'll do is 9 different evolutionary models, or 9 different kinds of models. And then you can do model comparison with them and pick out the best model, or you can do all those things you can do with model comparison. You can do Aki-Ike weights. You can do all of those things, right? It's all, it's not written. You'd have to probably roll it yourself. AICC is written in there, but you'd have to do your own Aki-Ike weights. But now you know how to do it. You know the equations. You could do it pretty easily if that's what you wanted to do. And so I think for all these reasons, this is why people are moving this way, right? And computationally, it's not taking 7 seconds on a VAX 8700, right? These are essentially instantaneous. Right? So there's no reason not to do this anymore. The tools are there. 10 years ago, the tools were not there. It was really hard to do. There were 5 different people trying to write PGLS in R.
Was the coding a challenge, or was it just still computational time?
No, it was the coding. Yeah, I was trying to... Which it turns out, I don't know why it took so long, because what you'll see is it's actually not that hard. We can do it in 3 slides here. So I don't know what actually was the holdup. There was a guy at Penn State who was working with Tim Ryan, and they were trying to write it. Well, the math guy was trying to write it, and Tim was trying to give him the data, and they were sending it to me for testing when I was, and this is when I was in Riverside in 2005. And it was very, I look back and I was looking at the code yesterday, why is this so convoluted, right? It's not really that, shouldn't be this hard. Anyway. All right, so let's look at how this works. And so again, we're going to start with this really simple example because we can actually see the entire matrix at once, right? So basically we're going to end up with a matrix that tells us something about how these 5 tips are related to each other. And so that matrix is going to be square. So in this case, it's going to be a 5 by 5 matrix. And so if you've got 20 taxa, it's going to be 20 by 20. If you've got 200 taxa, it's going to be 200 by 200. And then it's going to have 40,000 variables in it, right? 40,000 numbers in it because it's going to be square, the whole thing, right? So you would, really big trees, you would still run into a problem, right? And by really big, I mean hundreds of thousands, right? Because then because what we're going to do is invert that matrix. And that's always when you run out of memory. Basically, that's always been the big challenge with really, really big data sets. But for what we're doing, it's not going to be a problem. Okay, so this is in a Mesquite file, so we'll read it in. And then this is just the plot from last week. So we've got those nodes. Remember, we calculated for these 5 tips, we get these 4 nodes of independent contrast. We're not going to get contrast, right? We're going to work with the raw tip data, right? We don't have to do any sort of, there's none of these sort of intermediate calculations. We just use the data as it is. And then branch lengths, we've got a tree that's scaled to a total height of 1. And it's ultrametric, which means that all the tips line up. And this is actually going to be really important later on, especially when you deal with fossils, that you won't necessarily have ultrametric trees. You'll have lineages that persist for a while and then they go extinct. But if you've got extant taxa, then you're okay. And so these all add up. So 0.38 and 0.62, 0.38 and 0.13 and 0.49, right? So all these, basically everything lines up here at the end. So, all right, so far so good. This makes sense. And we're just going to enter the data manually, just because it's easier. These are the log values. And I'm just going to use X and Y instead of, these are longevity, or these are body mass and longevity. I'm just going to use X and Y because it'll make the equations that we're going to look at more general, right, with just X's and Y's instead of longevity and body mass. Right? So these could be arbitrary data. We could have just made up 5 numbers, and this would be the same. We don't actually need this, but I left it in there just to keep track of which values these go with. Our tree is coming in the reverse order with homo at the end, and so I'm just going to flip them around so there's a reverse function. So I'm just going to run them from back to front, just to because we have to make sure that the tree and the tip data, in this case, that the tree and the tip data are matched up in the same order, which won't be true when we use the functions, because as long as we set it up right, it'll make sure that everything matches up properly. But for our little manual example here, where we're working our way through this, we have to do that. All right, so far so good. We've got data and we've got a tree. Right? That's what we need. All right, so we're going to go backwards now. We're going to talk about general linear models. Right? And we're going to look at a slightly different way to express them, and we're going to see how they're actually solved inside of R. So these are all like OLS and ANOVA and t-tests and all those things, right? These are all general linear models. Hopefully this is all old hat to you at this point in the class. And there are assumptions, right? So we assume equal variances, right? That's a common assumption of things like ANOVA and t-tests. But it's also an assumption underlying regressions, because remember we assumed an equal spread around that best fit line, right? That all of those little normal distributions have the same shape, right? That's the assumption of equal variance. It relates to that. Critical though is that their covariances, or the correlations between the points, are 0, right? And this is another way of saying that they're independent of each other, right? That the value of one has no influence on the value of another. All right. We've dealt with actually this case before where we don't have equal variances. Remember when we did that squid example where like month to month the variances were changing? We'll see that actually one of the solutions to Pgls is the exact same solution that we use there, at least the same function. But it's basically doing the same thing. Covariances is going to be the main problem that we're going to solve here. Okay. All right, so let's look at this. So here's our old linear model. I've written it slightly differently now. So this is how we used to write it. It was like, beta naught plus x, beta 1 x. So I flipped them around and I've added a 1 out here. So you can imagine this beta 0 is multiplied by a bunch of 1s. You could also think of it as x to the 0, if that helps you, but if it doesn't help you, then don't think that way. All right. So that's our linear model. We can think of these rather than being sort of like an equation. We can think of this as actually a representation of the data. So that this y here is not just a single y value, but it's actually a column of all of our y observations. Right? So if you've taken other sort of more mathematical stats class, you probably have seen something that looks like this before. Has anyone seen something that looks like this before? That's good. People have spared you from that. It's not crazy, right? So here's a single y, but we got y1, y2, y3, all the way down. Those are all of our y's, right? So our observed values is a column of y's. And then all of our x variables, we only have 1 here, but we could have an arbitrary number of, x1, b1, x2, b2, x3, b3, right? should be familiar. Those all go into this matrix here. So it's got a column of ones. That's where this 1 comes from. So it's got a column of ones, right, which is going to be this. It's going to represent this term here. And then in this case, we would only have one of these, so we'd have just this column. But if we had lots of other x's out here, we could have x2 and x3 and x4 all the way up to k variables, right? So you think of this as a big matrix that has as many rows as you have observations and as many columns as you have variables plus 1 more for the intercept. If we had no intercept here, there would be no column of 1s here. So just, right, does that make sense? Okay, then there's another column of where all these betas go. So beta 1, beta 2, beta 3, and these correspond to, so this one here corresponds to this column, this one corresponds to this column, all the way down, right?
No beta, not?
No, because that's going to be this one here. Okay, and then that's the little error term that we usually leave out. So I have left it out up here, but the person who made this figure didn't. All right, so this is actually what happens inside of when you do LM. This is what's happening. Is that it turns the thing to the left of the tilde into this column of numbers. It basically makes a model matrix, which has all of this stuff in it. And then it's going to estimate. This is the part we don't know. Right? This is the piece that we don't know yet. That's what we're going to estimate here. Calculate, or however you want to look at it. All right, does that make sense? Just what the structure of the data looks like. Okay, so what's happening internally and what we're going to do here in a second is actually solve this directly. Right? We can actually we can calculate these beta coefficients by math. Right? And this was the matrix math that I spared you up until this point. So better or worse, here it is. So here's how it works. So B is not just going to be a single number, it's actually going to be all of the betas all at once. All right, and so did anybody actually watch the video about how to do matrix math? So it's really not that mysterious, right? It's multiplication and addition in a very specific order, right? So you multiply rows by columns and then add them up. And so you have to have the right, conformation. So you need the same number of rows in the first thing as columns in the second thing, or else they won't go together. All right, and here's the equation. This is it. It's deceptively simple. So x prime is just the transpose of x. You just flip the rows and columns. So x prime times x. So you transpose it, multiply it by itself. Matrix algebra, not regular. And then this -1 does not mean divide by 1. It means it's called the inverse of the matrix. And you get it, there's a function in R called solve, which if you give it a matrix and tell it to solve it, it will give you the inverse. If you actually want to see how to manually calculate the inverse, here's another link. You don't do this. You can do it for like a 2x2 or a 3x3, but beyond that, you don't manually take inverses of matrices. But it's not, again, it's multiplication and addition in a very specific orderly way. That's all it is, but we don't need to know how it does it. All right, so we multiply that by, again, the transpose of x times y, and that's it. All right, so let's set up our data and make this go. So here's our y's. I'm just going to make our y variable values into a single column matrix. So matrix column of 1, so there's our y's. And then our x's, I'm going to have x, I'm going to bind a set of 1s to it. So this is going to make, sorry, let me go back. This is going to put the 1s and then all of our x values, right? So we've got a column of 1s and a column of our observed x's, right? Straightforward. All right, so let's solve it. All right, so in R, this percent x times percent does matrix. Otherwise, it just multiplies element-wise. So again, you're not going to have to do this, but that's just what's happening here. All right, so this first part, that's this right here. That's all that stuff. So we're going to solve the transpose of x1 times x1. And then we're going to multiply all of that stuff by the transpose of x1 times y. And if we run that one line, we get this value. We get this. right? 2.59 and 0.34. Right, so it spits out the B that we were solving for is it's got 2 rows, 1 column, and those are these are these 2 betas right here. All right, does that make sense? And if we do it as an LM, right, so now we're not going to use the one that has the 1s in it. We're gonna put the column of 1s over here. We get the coefficients, the intercept 2.598, and x is 3.42. Right? So we get the same number. So are we satisfied that this actually works? That it is that simple, actually? LM's doing a whole bunch of other stuff, right? So it's calculating a whole bunch of stuff at the same time that it's going to let you do, all the hypothesis testing and the R-squared and all that other stuff that goes along with it. But if all you want is like the fastest way to solve a regression, it's this. So this might be useful to you someday when you have to do, tens of thousands or millions of regressions, right? If you do it this way, this is about as fast as it goes. You can't speed it up. And people have figured that out. There are packages called FastLM, which basically does this. It's like no frills LM. You get nothing. You get none of the other stuff. But if all you want are the coefficients, it's the fast way to go. All right, so this has only to this point proven that we can do linear models by hand. All right, so now we're going to build on this and try to get to generalized least squares, and then we're going to get to phylogenetic generalized least squares. So we're going to get to GLS and then to PGLS. Okay, so to do that, we need to first get this matrix of the tree in there somehow. Right? So we need to first get something in there that we're just going to use right now just as a placeholder for our tree. Because later on we're going to replace it with the tree, but we want to make sure we can get the math to work before we stick the tree in and change. We don't want to change 2 things at once, basically. So let's just change 1 thing. And so the best way to change only 1 thing at a time is to multiply something by 1. Right? And so if we're going to multiply a matrix by 1, we can't just use 1 because that will give us, that's not matrix multiplication, that's just regular multiplication. So we'll use this thing called the identity matrix, which is, again, a square matrix with a 1s down the diagonal, and then everything else is zeros. So we go off diagonal through zeros. And so if we multiply this, so again, if we take the transpose of x1 matrix, multiply it by our identity matrix, we get itself. So that's what this is. Right, so we've transposed it just so it would fit on the page, and then I multiply it by 1. So this is the matrix math equivalent of multiplying by 1. Right? So it's just not very exciting, I admit, at this point. But this is going to allow us to set up a framework that we can then make the leap into phylogenetic regression here. All right, so we can use this matrix as what's called a correlation structure. And so we're going to call it W in this case, as weights. But it's not, I don't really want to call it weights because weights is going to be something else when we get to the functions that actually do this. So it's a little bit different. But basically we multiply all of the stuff in here by that matrix. So and again, in this case, we're multiplying only by 1, essentially the identity matrix. It doesn't go in as is, though. We have to do a little bit of repurposing. So we need to put in something called the decomposition. Again, decomposition, something that you won't want to calculate by hand, but there are videos online where you can learn how to calculate decompositions. We're going to use one that's called the Cholesky decomposition. Again, it's not important why. So we're going to get the inverse with solve, and then we're going to get the decomposition of that inverse. And this is what's going to go in. That's actually what's going to go in here. So we're not going to put I in directly. We're going to put in this thing. And the identity matrix has this great property where the decomposition of it is itself and the inverse of it is itself. So again, it's like 1. It's like everything is 1 here. So it's going to let us stick it in here and nothing should change. Right? That's what should happen. You with me so far? All right. Rather than making this solve that 1 line really, really long, we'll just go ahead and do the transformation here, and we'll call it xtr for the transformation of x. So we're going to multiply the, so we're going to take the inverse and then the decomposition, multiply that by x1, and then we're going to do the same thing for y, okay? And those are going to be the exact same numbers. At least they should be. They will be, because I know they are. Okay. And if we do that, we put in the transformations of these instead, we once again get the same numbers. Okay, good. So now we can stick a matrix in there. And as long as that matrix is identity, we get the same answer. So now we're set up. We can do it. We can put in a matrix that tells us something about how things are related to other things. And this is where the tree is going to come in. So far, so good. All right, so let's look at a real correlation structure. Okay, so we're not going to transform by, a bunch of ones, right? We're going to put in things that don't have zeros in the off diagonals, right? So we want things that are going to, this will basically allow us to have covariation between observations, right? And this will allow us to then weight them, right? This is essentially what we were doing with the squid data, right? So we were allowing the variances in months that had the same value to be more similar to each other. That's all we were doing there, right? And that solved our problem of these exploding variances, right? Same idea here. Okay, so what are we going to use? We go back to Garland. Remember, this is when we were talking about adequate branch length transformations. They say that, when we're talking about standardization, they say that the goal here is to receive equal weighting, right? And that's what we want to do. So we need a matrix that has off diagonals which tell us how similar the tips should be based on phylogenetic relationships. And so under Brownian motion models, which again is the simplest, right, that's proportional to the shared branch length between those two tips. So how much of evolutionary time do those two tips share with each other? All right. So this matrix that we're going to use is called the phylogenetic covariance matrix. There's a function VCV philo, right, which gives you the variance covariance matrix of a tree. So there's our tree object here, primates. And we're going to call that VCV over here. And so this is what it looks like for primates. And so where does this name come from? So the variance is a measure of how much the species have diverged from the root. So essentially the time to the tip for each one. And that's down the diagonal. So for this tree, we have a total height of 1, and all the tips line up. So these values are all 1. So from Galago to Galago, right, the whole distance to that tip is 1 unit. And then
from the root.
From the root, yeah, exactly. So from the root to the tip. And so all these values are the same because we have an ultrametric tree. If our tree isn't ultrametric, they're not all going to be 1, right? Because some are going to have less time than others, because some will go all the way to the tip and all the way to the end, and some will only go part way and then go extinct. Then the covariance part of this variance covariance matrix is how much they resemble each other, and that's the off diagonals. Right, and these are in this case, it's really simple. It's just the shared length between tip pairs. That's all it is. And I'll show you in a sec. The next slide has the tree, so we'll actually see where these come from. So, and you can see that it's symmetrical. So Ateles to macaca is the same as macaca to Ateles. So the upper and lower triangles are going to be the same here. Okay, so let's look at this. So let's see. So where do we want to start? What? Pongo homo. Okay, so 0.79. Whoops, go forward. All right, so Pongo and homo, right? So to get to this pair, 0.38 plus 0.13, so that's 0.51, plus 0.28, and then they diverge. So that should be 0.79. 78. 79. Okay. That's all it is. Right? So we have to, so we could actually calculate this manually. We just have to go up each branch. For every pair, we'd have to basically trace it backwards, chop off this piece, and then see how much of this shared time they, but I spared you that exercise. I figured we didn't need to do that one. We can get that here from this VCV philo. Okay, that's all it is. So that's going to be our identity matrix that we're going to stick in there, and it should do the job.
It's always that, even if it doesn't add up to 1.
Exactly. Yeah. So it's always this, even if it doesn't add up to 1.
It's not ultrametric.
Yes, correct. Even if it's not ultrametric, that's correct. It's always going to be this shared time. Yep. Okay. All right. So we can do that. I've just sort of separated this out a little bit. So we can take that VCV matrix. That's what we just did. That was this guy here. Right. This 5 by 5 matrix. And we're going to solve it, and then we're going to plug the inverse of that into this Cholesky decomposition, and so there's our VCV root. Right? So that's going to be our transformation matrix. We multiply that by x1 and by y, save those, and now we can just plug that in. This is the same equation we used before. Just copied it and pasted it here, and we get a new set of beta estimates. 2.5 for an intercept, 0.432 for a slope. And that's it. That's all the Pgls does. All right, so there's nothing like magical or mysterious about it. It's really just taking the observed data and then transforming it based on how similar you expect those data points to be, and then solving the equations. So we could do this manually if we wanted to. Again, we're not going to. But the point is that you now know what this is doing, right? There's nothing special about it. And hopefully you see at this point the power of, well, now if we modify these branch lengths, we modify the shared evolutionary time, that's going to change this matrix, and now we can include different models of evolution really, really flexibly. You made that leap yet? You will soon. All right, that's it. All right, so let's see this in the way that you would actually do this in real life without actually going through and doing it manually. All right, so let's just go back. We'll put the data and the tree together. I'm going to make one of these comparative data objects where it sticks the trees and the data. Tree and the data go into one. This is how we're going to do it mostly. One of the two main ways that you'll do PGLS and R. Tell it that species is the column that contains our tip data. And so in this case, we don't have to worry about the ordering because this is going to take care of it. It will figure out how to get the tips in the tree in the right order to each other. So this is why you would use functions to do this rather than doing it yourself. So PGLS function, right, looks a lot like LM, right, where we put here's our outcome variable, is modeled by, in this case we're only modeling it by x. We don't need to take out the intercept here because we're not dealing with independent contrast. So we're going to estimate an intercept. And then we're going to use that comparative data object. And we get numerically equal, I hope. Better be. Right, it has to be, right? It can't be not. We get the same numbers, right? So it's doing the same thing, except that it's saving us all of the other trouble, right? It's adding the column of ones, and it's doing the matrix math and all that stuff. It's figuring out how to deal with the formula, right? We can do it manually for a very, very simple model, but if we wanted to have more complicated models, it would be a lot, like the effort that would go into it quickly outweighs the reward that we would get from it, right? But if a simple example works, then everything else should work. We can be confident of that. All right.
So if BIC does not allow intercept, how are these numerically simplified?
The slopes are identical. So this part is, and then you can go back with that slope and the independent contrast. You can go back and figure out what that intercept should be. The essentially un-PIC'd intercept. No, it's not. It's not parallel. It's just, so think about if you force it through the intercept, it's sliding up and down, right? And so. Oh well, yeah, it's yeah. I see what you mean. Yes, parallel. I was thinking of some other context of parallel, which is coming up soon. It's later. Anyway, so you can go back and back calculate, and this is what people knew for a long time, was that those numbers were identical as far as we could tell, but we didn't know that they were identical, that they were the same number. So this is actually how you would do it, right? And you wouldn't even manually enter the data, right? You pull your data in from an Excel file. You pull your tree in from Mesquite, and then it's like one step to here. Although we'll do a lot more checks, particularly when you work through the problem set, especially. We'll do a lot of checks to make sure that everything is there. We'll trim down the tree to make sure that the tree only has data that's in your file. Trim down your file so that it only has complete cases that are in the tree, right? So just basically probably a lot more error checking than we would normally do. You will run into problems if you have, tips that aren't represented in the data or vice versa. Well, vice versa is probably not as much of an issue, but I would say better to not tempt it, right? So LM and other functions like that in R will just silently drop missing data and not tell you about it. So if you have like incomplete data, it just leaves it out and doesn't say anything about it, which is probably not the best thing, but the way that they wrote it, and I can't complain about it. These methods might not do that, and it might give you weird answers that you don't expect. All right, so we can now play with rescaling trees. So we can go back and actually do this lambda transformation. Remember what lambda does is it tells you, it has a measure of how much the variation at the tips matches what you would expect under a Brownian motion model. But it's also a way that we can rescale. We can basically grab the branches and slide them around. And if we rescale it to a very small value of lambda, we basically grab all the tips and slide them down. So essentially, there are very, very, very short branch lengths in here, but they're very short. So it's not a polytomy. It actually has structure to it, but you just can't see it because of the scale. So I've rescaled this tree to we call it star phylogeny. So essentially, where all the tips radiate from a single point. And so hopefully you can guess what the variance covariance matrix is going to look like here. All right, so we're going to have 1 down the diagonals because they all still have a height of 1. But these off diagonals are all very small values. Right? And they're actually very small values in a very particular way. All right, so if we go back and look at our original tree, we had like 0.38, 0.51, 0.79. And now we have 0.00038, 00051, 00079. We have simply divided through by 0.001. Right? And that's all the lambda transformation does. It is literally divides through by lambda. So lambda equals 1 divides through by 1. So lambda 1 equals. All right, so if we run this through, we should now get the value that pretty much approximates the non-phylogenetic regression, right? And it turns out that we do, at least down to a few decimal places. Does that make sense? All right, so this proves Ted's point that regular regression on comparative data is really just a special case of phylogenetic regression. It's subsumed all of linear models for Pgls here. All right, so that's good. That means that we can stick any sort of a transformation in there and be confident that we know what we're doing here. As long as we know what that transformation is doing, what it's going to make the branch lengths look like, then we know that this is what's going to happen here. Okay, so there's a couple other ways to do this on Pgls-like approaches. So we're going to use, in addition to Pgls, I'll show you how to use this in the GLS function in LME. This is the one that we use to solve the squid problem. There's a parameter in there you pass called the correlation, where we are going to somehow pass the tree in there somehow. We'll see how to do that. There's a thing called generalized estimating equations, which I have not talked about in this class. But there's a comparative, in the 8 package, there's a compare G, which does this. Does these for phylogenetic models. It's a lot like a GLM, so like generalized linear models. So this is one way that you can do non-Gaussian outcome variables, particularly logistic regression. This is the way you would do logistic. There's a MCMC method you can do. This does phylogenetic GLMs. This also is really handy for doing pedigrees. So if you have like animals that are related to each other to varying extent, and you want to take into account those relationships, this is another way to do it. There's a bunch of other ones that can do it. I don't know. I came up with 5 off the top of my head, but you won't use them because they're not as useful as these other ones. So, including the one that Graffin wrote, the one that Tim Ryan and or the other person who was working on it were. There's a bunch of different ones. There's one in PhiTools. They're, I find, less friendly than these other ones. Actually, Pgls is the most friendly, but it doesn't do OU models, which is why, so it's a little bit frustrating there because I frequently like those. All right, so let's work on an example here with Pgls to sort of see how you would do a more complete analysis that isn't just 5 species. So there's basically 2 steps. We got to make this comparative data object. It takes care of some of the dropping of tips and things. I still recommend doing it yourself just to be sure, just so you know what tree is going into it. So do all the setup. Once you work through the problem set for this week, you'll see how to do all of that stuff, how to figure out what tips are in the data and what data are in the tree, and get everything stripped out that shouldn't be there, so that all you have is the stuff that you need. We can estimate. We can actually enforce a branch length transformation, right? So we could do a Pgls lambda of 0.001 if we want to, or, and this is the real power, is we can actually estimate one at the same time while fitting the model, and that's what we're going to do. That's the much more common usage. We can then fit models. It calculates AICs and AICCs and all that good stuff that we want, and so we can just extract all of that stuff right off the top. All right, so the 3 different evolutionary models it can do. So it can do a Pgls lambda. So again, 0 is a star, 1 is Brownian motion, and then don't go above 1. It's basically bounded by 0 and 1. It can estimate a different scaling parameter called kappa, which has to do with it's a speciational model. So it basically takes into account the number of branching events in between pairs of species as a metric for diversification. Right, so this is kind of like a punctuated equilibrium sort of model. So if there are lots and lots of speciation events between a pair, it assumes that evolution is happening more rapidly in that range. And then it can estimate delta, which is a time-dependent model, kind of like an AC/DC model, right? So either an accelerating or decelerating through time. And again, all of these things, all of these transformations, they leave the tips in the same place, they leave the root in the same place, and all they're doing is sliding the nodes around. Sliding them up toward the tips, sliding them down, and sometimes they're not sliding them linearly, right? So they're not all moving together in the sense that long branches, right? So if you think about it like a log or an exponent, right? The long branches get even longer than the short branches, right? So all these, that's basically what all these things are doing. So, all right, so we'll use this example. This is a data on heart position in snakes. This actually, you may not be aware, is a very hotly debated topic. Actually, there's this paper came out, and then there were several different, several letters to the editor, and then there were several different rebuttals by the authors. Why do we care?
No.
Debate.
Can
we not just open it and see where the heart is?
I mean, what segment it's in or something?
Yeah, where is it relative to the head?
Yeah.
So here's the thing. So snakes spend a lot of time vertical, and so the idea is that if getting blood to your head is a big deal, and so if you put your heart a long way from your head, it's harder to. You might need more. It might take more energy to pump it to your head, and so if you spend a lot of time vertically, so if you were arboreal, for example, then it would be energetically advantageous to have your heart close to your head, as opposed to further away. A lot of internal organs in snakes get moved around. They only have one lung. There's all these problems with snakes because they're so tube-like, And then there are snakes that are aquatic, which would presumably remove some of that potential constraint. So it actually is a really interesting question. And Gabe Gartner was a student. He's a herp guy, a student of Ted's. And this was actually his project for the phylogenetic comparative methods class, which actually is where this started. It was funny, from that year, there were three of the analyses got published, actually. There was one on scale number in lizards, which actually is another really interesting, hotly debated, and then brain size evolution in cetaceans, which has obvious interest to people. So yeah, there are actually three, and then there's still one that I'm working on that probably will never get published. Although now actually the methods for doing it exist, right? Because we need a way to needed a way not just to randomly shuffle the tips, but we need a way to randomly shuffle the entire tree to come up with a null tree. But now there actually are ways to do that. So anyway, so that's what we're dealing with. It's a huge data set. You can see there's lots of polytomies in it, though, right? So there's some unresolved branches here. So there are 155 species, which is, again, it's a crazy number of, and these are, it's a funky tree because it actually has these this was all done in DOS still. So we're stuck with two character tip labels, so it's completely useless, the tip labels at least. But there's a code in the data file that matches the tips to the data. And these are log snout vent length and log snout heart length, so the distance. So this is, snout heart length is always going to be less than snout vent length. And then we've got
Like trailing.
Heart, tail heart.
so then we've got habitat, so it's a factor with 5 levels, so aquatic, arboreal, I think there's like, I don't know, you can see the plot here in a second. And then families, so you can actually code families. And this is another benefit of using Pgls is that you could say, well, what if I think that this family has undergone is like a different scaling pattern or a different relationship just in this one group within my tree, right? And that's another sort of powerful thing you can do here. This is what the tree looks like. I took the tips off because they were useless. These are set to arbitrary branch lengths. All right. So here's what the data looks like. These are habitat, so aquatic, arboreal, fossorial, so underground, semi-aquatic, and terrestrial. The colors didn't turn out well. But then if you actually code family by the shape, you can see there's actually structure in here. So all the viperids fall up here. So there's a long distance to the heart, relatively speaking, from, on a per snout vent length basis, they actually have, the heart is located further posteriorly, right? So this is actually, just looking at this, you'd say, this suggests that we really need to deal with the phylogeny here, right? Because there appears to be very, very apparent phylogenetic structure to these data. Okay, so we're going to create this comparative data object. So it's really simple. We just put our tree, the data, the names are in tip code. And then I've had to add this because we're going to do the kappa transformation, we need a 3-dimensional variance covariance matrix. So that's why I put this line in there, so you know. And this is what it looks like, right? So it's got the tree, it's got a VCB matrix, which is 1 by 155, and then it has this extra column. And then here's our data. And so we can basically use any of these data. I've stripped out all the other non-interesting stuff from the data set. We can use any of these in our PGLS. Right, so we could code anything we want. We can look for single outliers. We can look for like unique evolutionary events, which actually you can do with phylogenetic methods. Right, you just code like one tip in its own category, and then you can see whether that tip does something different. It works. All right, so we're going to compare a bunch of different models. And so this is model 1. Snout heart length model by snout vent length with a Brownian motion model. Right, so the simplest model we can fit. This is essentially, right, this is regression just through all these points, right? As you would, a regular OLS regression here. All right. And so you can see the summary, we get a lot of the same stuff. We get residuals, right, which you can interpret more or less like you would residuals. They're kind of these are phylogenetic residuals, so they're a little bit different, but that's okay. If you were to do a branch length transformation, these are all basically saying this just says we didn't do anything. By default, all of these are 1, which means no transformation. And we get a block of coefficients just like you usually do. And so we get an estimate of the inner log position. So this is a length and a length. So we expect the sort of isometric scaling relationship to be about 1. And we could go in and actually do what am I trying to think of? What's the word? What do we do with this? we do the slope test on it. My guess is it's going to be, right, so that isometrically that should be like 1. You'd have to manually do it yourself, but divided by the standard errors, that's like 0.08 divided by 0.03 is what? About 2 point something? Yeah, so it's probably not, this is probably significantly negatively isometric. That'd be my guess, just based on a seat of the pants calculation of the confidence interval. But, right, which means the bigger snakes have hearts closer to their heads, which again might make sense. This is again taking out phylogeny. So now we have a phylogenetic independent estimate here. So that's one model. We could put in snout vent length plus habitat. So now we get an estimate for snout vent length, and now we get, because it's gone in as an additive model, this is going to fit this same linear relationship, but it's going to offset all of the intercepts. And so we can see that none of these are significantly different from the base, which is aquatic, I think. It doesn't have this sort of nice convenience of doing like an overall ANOVA sort of thing for all of these. There's an ANOVA method, but I couldn't get it to work very well, so I think you'd probably have to roll that part yourself. But for now, we can at least compare the models, and that'll get us somewhere. Here's a model where we do snout vent length with a lambda transformation. And so we're going to fit a lambda parameter by maximum likelihood. So it's basically going to estimate lambda. It's going to find the lambda that minimizes the variance at the tips. Okay, so what does that mean? You've got your tree, and you've got your observed data. You calculate the amount of variation at the tips. Right? Then you can transform the tree and figure out what the expected now variation is. Right? And there's a transformation in there that minimizes that variation, the variance. That's the lambda transformation. That's what all these are doing. Okay, so we estimate that, and so you see now we get some difference in here. So now we get this stuff. So now it's estimated lambda by maximum likelihood. Its value is 0.736. So 1 is Brownian motion, 0 is the star phylogeny. And so what we're saying, this is a pretty common occurrence, is that you find some value of lambda or the alpha parameter of an OU is something less than Brownian motion, right? Which suggests that there's some selection going on in there, right? That's really what the implication is. So people would frequently take this, especially the fact that the confidence interval does not overlap 1, as evidence for quote phylogenetic signal in this data set. We'll talk about a lot more about phylogenetic signal on Friday and kind of what that is. But that's what this implication is that there is some, the variance or the variation at the tips is less than what you would expect by Brownian motion, which suggests that there is some sort of selection going on here, right? Or that there is some kind of constraint. But that, again, Ted bristles at saying constraint, so I've been conditioned not to say phylogenetic inertia. Like I wouldn't say that either. It's simply variation, right? There's less variation at the tips than you would expect there to be, and for whatever reason, right? And that reason might be selection. And we can leave it at that. We could look at these coefficients. What I want to do is actually fit a bunch more models and then actually pick the one that fits the data best. So here's a kappa. Remember, this is that speciational model. I didn't fit the AC/DC model in this case because it doesn't, it's not like the arbitrary branch length. It doesn't make a lot of sense. It didn't seem to make sense to me when I was putting this together the other day. And so again, this is estimated at something between 0 and 1. This one actually was bounded by 0 and 3. But we get something closer to a star, which suggests that there's less variation there than we would expect. And we can keep going, right? We can put in family instead. We could put interactions if we want. We could put family and, right? We could essentially do all of them if we wanted. And I didn't do all of them, but we could put other predictors in. We could do whatever. So I just did these 9. So here's this snout vent length only, snout vent length plus habitat, snout vent length plus family, and Brownian motion, Pgls lambda, and the speciational model. And these are all the AICC values we pulled out. And we can use our usual, smallest is best. And so in this case, I think that one is the best. So it's got, and these can be negative, that's okay. It's just whichever is the biggest negative number in this case. So among all of them, this is the best one. Right, so log snout vent length plus habitat with a lambda transformation is the best one. So then that's the model that you would go, right, or you could do Aka-Ike weights, you could do all that stuff, but that's probably the model that you would then say fits better. And it seems to fit better than, there's a big jump between that and the next best model, which is this one here. I mean, that's like 10 units, right, 10 AICC units, which is that's a huge jump, right? So this, if you did the weights, this would get all the weight almost, like probably like 95% of the weight in this case.
It's sort of like an ANCOVA, I guess.
Yeah, this is an ANCOVA, exactly. Because we fit, this is a continuous, and we probably should stick the interaction in there. And these get penalized in the same way that other models get penalized, right? By estimating lambda, you're estimating another parameter. So that gets penalized just the same way.
Brownian motion?
Brownian motion doesn't get penalized because it's yeah. Or it would get, I mean, it's more than Brownian motion. Yeah, I don't know whether actually there's a penalty. There may actually be a penalty for Brownian motion, actually, like a penalty of 1 or something. But we could fit the OLS, if I could stick the OLS in here.
That's a good point. Phylogenetic, including phylogenetic data and all, is that already?
Yeah, you've already incurred a
penalty for having more input data or whatever.
Yeah, although you're not really estimating anything. I don't know. I'd have to actually check that to be sure. I don't know. I'll look at it and see. So the big sort of hindrance here is that we can't do OU transformations, which I have a particular fondness for. I just like them as an evolutionary biologist. They make sense to me. And so for that we have to use the other main workhorse for PGLS in R, which is the GLS function. Here's our best supported model again. So this would be this snout vent length plus habitat model plus a lambda, right? And so it's lambda's maximum likelihood. Yeah, you'll see that a lot, ML. The other thing you'll see is REML, REML, which is the restricted maximum likelihood, which works slightly differently, but you don't need to worry about the details of that. This basically just says, so you could put a number in here, right? You could put 1 or 0 or something in there, and it would just do the transformation. But by putting an ML, it estimates it. So you could go in, you could put in 0.698 up here, and you would get these same estimates out down here, right? Which is how we're going to solve one problem with OU regression here in a second. So then you would go on, like you would then say this would be the model that you describe. And if you actually go and read the paper, they actually do a bunch of other different things here, and then they talk about different models getting different amounts of support, and the best model is probably actually something with habitat and family in it. There's a lot of family structure, but then there's habitat, but those co-vary with each other, right? They're not completely overlapping, but right. So families tend to have similar ecologies, so there's something to that. It's a good paper. It's actually worth reading. If you end up doing this sort of thing, it's a very methodical. It's actually very clearly explained all the way through what like all the steps are. If you just don't do it in DOS like they do, and do it in R, it's much better. But in terms of actually we did this because of this, and then we tested this, and this is what we found, and this is what it means. It's very it's actually partly because it was written by a student. There's a very logical flow through it, which is actually good because if people skip those steps, right, if they don't have to sort of think through them in their head. All right, so let's look at last bits here. Let's look at a GLS, which is in the NLME package. This is the one that we did the SQUID model with, right, where we had a correlated variance structure per month, right? That was the problem you're solving there. Right, basically, we're doing the same thing. This is it's a similar solution to a different question. And so here we have to choose, to work with GLS, we need to get a phylogenetic correlation structure, which there'll be some similar options that we had to PGLS, but there's going to be one big difference, or a couple of big differences here. So these are what they call core classes. You can look at the help for core classes if you want to read more about it. So core Brownian is the Brownian motion model. That's going to be the standard. Pagel is Pagel's lambda. That's pretty standard too. Core Martins does the OU model. So this was originally Martins and Hansen, which was similar. It wasn't quite exactly the same thing as Blomberg 2003, but they're pretty similar, at least similar enough. So this is going to estimate the strength of selection, right? So that's what that's going to estimate. Core Blomberg actually does the AC/DC model, and then Core Graphene does Graphene's rho. And so this is a transformation that we haven't talked about yet. This essentially is an exponential transformation. This was like originally, this was a transformation that Graphene originally talked about. If you want to like futz around with all these, it's actually worth just opening up, get a tree open in Mesquite, and you can, all of these branch length transformations are in Mesquite, and just play around with them and just see what it does to your tree. Do it, undo, do a different one, undo, put in different values for row.
And why are we talking about transforming branch lengths? I mean, if we have meaningful branch lengths,
Because our meaningful branch lengths might not adequately standardize the tip values.
oh, for like equal variance.
Yeah, for equal variances, yeah. And so these will estimate. They also don't, if you have good tip values, I mean, if you've got good branch lengths, it still doesn't tell you anything about it. By doing this, you can test evolutionary hypotheses. That's the other main benefit here. So there's the practical side of properly standardizing, then the interesting question side to me, which is evolutionary. So let's look at these Graphene's rho transformations. These came out really tiny for some reason, sorry. So rho equals 1 is just base branch lengths. Rho 0.5, basically it takes the small branches, which are typically going to be out here, and it drags them toward the root. And you can see the sort of extreme of that as they're getting longer and longer. So this is going to, again, sort of approximate a really small lambda value. Higher values take long branches and make them even longer, right? So this very long branch here gets pushed way out, right? So it makes this one branch really long, and then these little branches in here get kind of squished. They're not getting squished so much as they're not getting expanded nearly as much, right? So that's what rho does. So you'll come across this. This is an old transformation, and so you'll come across, especially reading older papers, people doing Graphene's rho transformations. Okay, so let's go back to our original question from last week, where we talked about mammal home range and body mass. So this was the original data here, and so this is just loading it in, stripping out some weird characters in the tip labels, and then loading up the data and refactoring, releveling clade to ungulates first. So here's our tree. Right, all the ungulates up here, carnivores here. And then here's what the data looks like. And so again, if we were just doing this non-phylogenetically, right, you would probably fit a single line through all those points. You'd fit parallel lines through ungulates and carnivorans, and you'd probably fit separate lines for the two and compare all those different OLS and ANCOVA models, and you would almost certainly find that the best model is parallel slopes between them, but those slopes are offset significantly. Right? Just eyeballing it, that's what you'll find, I think. But there's structure in here, right? So both in body mass and in home range, right? So these sheep up here at the top are probably going to be similar in home range size, and they're probably going to be pretty similar in body mass. Certainly more so than they are to this giraffe down here, right? Well, certainly in body mass, because a sheep and a giraffe are very different in body mass. Right? They'd have to be. All right, so we got to do a little bit more setup here. So we need to tell GLS where the tips are. And so we have to do one more step before we get to using this. If you don't, you'll get this message, which is like, tells you what it means, right? Row names in the data frame do not match the tree tip names. Data taken to be in the same order as the tree, right? So this is going to assume that the data and the tree are in the same order, which again, we don't want to make that assumption. The solution is very simple. We just supply row names. And we supply species as the row names. And now we have, instead of 1, 2, 3, 4, 5, we get the tip names as the row names, and then this will allow it to match up everything properly. And everything will work. That's all we got to do. So this is different. We supplied species when we made our comparative data object. We supplied species as to the function that made that, and that's how it knew where everything should go. But we have to do it manually here. All right, so here's how we do it. So again, we're going to fit a bunch of different models, and I'll show you how we can then sort of compare them in the same way. So we're going to use GLS, and again, it's just standard, just like you would for an LM. Data comes from here, and then we supply this next line, which is how the tree gets in there. Right? And so the correlation has a core Brownian where the phylogeny is the tree. Right? And our tree here is called tree. We could save this out. Sometimes you'll see if you're looking at like a tutorial or something online where they'll like save this piece as a separate, there'll be a line up here where this thing gets assigned and then the correlation just goes, plugs that thing in. But I don't know why you wouldn't just do it in one step. So here is where we would change, we could change core Brownian to core Graphene or core whatever, right? That's where we would do that. That's how the correlation structure enters into this. All right, so here's what it looks like. This is what the summary looks like. So generalized least squares fit by Remel, so a restricted maximum likelihood. And if you fit it with ML, you could do GLS, and you could do method equals ML, and you get very slightly different answers, but they're not going to matter. Here's an AIC and BIC, which I know we probably mentioned it from time to time. Here's the likelihood. Here's the correlation structure. Right? So we've estimated nothing. Right? So later on we'll estimate things. Here's our coefficients. Right? So here's the mass. Here's the slope. Here's the intercept. I actually have these values are like tattooed in my brain now because like 1.26 and negative 1.42. That means it worked. Right? This is the standard data set I use on everything to make sure that it works because I know those values. So I can get those and I know it works. Residuals, the usual stuff here, right? And so that would be a model if we were, this is akin to a phylogenetic OLS model. That's essentially what we have fit here. And we could pull out the AIC. We've got a lot of data here, 49, so AIC and AICC are going to be very similar, so we don't really need to, we could manually do that translation, but I don't think we need to in this case. Okay, so let's do another model. So this is mass and clade, again with Brownian motion. So this would be a separate intercepts but constrained slopes model. So an ANCOVA model with just allowing the intercepts for a different intercept for each clade. And so here's what we get. Right, so we actually we get a non-significant difference between the intercepts of those two. So interesting. With a Brownian motion model. So again, we probably want to compare lots of different models here. And if we compare AICs, this is like 94.4 and 92.1, right? So they're actually not that different, which is telling us that adding this clade doesn't really get us much, right? It gets, we shift by 2 units of AIC, but we're estimating another parameter, so it's basically kind of offsetting. We get a little bit better fit, but we're getting penalized a little bit. Right? So it's essentially offsetting our 4 that we would get. We're going back by 1 more. We can fit the interaction. Now we're fitting a model that has different slopes between the 2 groups. And again, this is where you would go down and look at this line, which is the difference in slope for being in the carnivoran group, and that's not different, which says that this model is not better than the previous model. Right? And we could do these as these are actually all nested, so we could do likelihood ratio tests if we wanted to. But that doesn't work. As soon as we start doing different evolutionary models, they become not nested anymore, and we can't do that. And if we were going to do that, we would probably actually not fit them by Remel. We'd fit them by maximum likelihood. But if we use AIC, then everything should be fine. All right, so OU. So we can fit an OU model with GLS. It's a little bit tricky. It's a problem that has persisted for many, many years and is yet to be solved. So I solved it for something I was trying to do a long time ago, and then this is just what I use now. And so basically what we got to do, you get this weird message, you get this weird error that doesn't make any sense, where if you try to estimate the OU, so you do core Martins, which is the OU parameter, and you want to have it estimate alpha. It will fail, and it will give you this error that says error in core factor core struct object. And it means like this is like completely useless error message, which basically means that it's not working. So basically what we have to do this in 2 steps. We have to do what I would call the brute force optimization of the OU alpha parameter, where basically we're going to fit a whole bunch of different models with a whole bunch of fixed OU alpha parameters, and then we're going to find the best one. Then we're going to plug that value in to GLS and have it fit it, and it will work. We know it will work. This is why, like, this is sort of like when I said back here that we could take this, say we could take this lambda value out, plug it in up here, and we would get these same numbers. We're basically going to do that. We're going to do this step of estimating separately. That's all we're going to do here. So this is how you would fit an OU model. So this little function, basically it takes some alpha value, some data, and a tree. And then this is not general. This is specific to this problem because it's going to fit log home range by log mass. It's going to fit, here's where the data comes from. It's going to use a fixed alpha value, and then it's going to return this. And all it's going to do is return the likelihood, right? So what we're going to do is maximize the likelihood with this optimize function. So we're going to optimize over the interval of 0 to 2. So from, right, so 0 selection to very strong, and then we're going to maximize it. And if we run this, we get a maximum value in this case of 0.012, which is actually pretty weak selection. So that alpha value, which is the strength of selection, is actually pretty weak in this case.
Is there a way to interpret 0.012? Like, that's not the kind of classic selection coefficient from population genetics, is it?
No, not like a heritability kind of thing.
Does it mean, I mean, how do you?
No, so if you think about that equation, remember the equation is alpha times, and then in parentheses it's like theta minus the trait value right now. Yeah. So it's basically this. It's the scaling parameter of how far away you are from the. Right. So it's really if alpha is really big, it's going to weight that very highly.
Yeah.
And if it's small, it's going to weight it not very highly.
It just doesn't have any units or it's like a proportion or anything.
No, it's not even a proportion because it can go above 1.
Okay.
It's got to be above. It's only bounded by 0.
Okay.
It can't be negative, I think. That would be weird. It would be like you walk away from the. You're going away from the optimum or something. I don't know. The objective is just the likelihood. So that's the thing that gets maximized. And so if we run this, basically we just have to run this in one step, get this value, and then we're going to plug that in. That's all we're doing here. And so I can plug that in here. And then here I'm doing it in 2 steps. So the OU model is Core-Martin's. The value comes from the maximum value of our alpha parameter, which is that's just this value here, the thing we were trying to maximize. And here's the tree, and then we fixed equals true basically says don't estimate anything. You can actually, if you started in the right place, the problem is, here's what the issue is that it can't figure out the right starting values. And so it doesn't know where to start, and it gets lost. And so if you actually start it really close to where it should be, then it finds the right optimum. But it's not very smart. So if it starts out far away, it can't get there. But once you found it, right? If you set it to like 0.01, it would find 0.01209, right? It would find the right place. But since you've already estimated it, you know what it is. So there's no reason to not just use it. All right, so we fit that. Again, we're just going to plug in OU mod down here. This is the other way to do it. Otherwise, it looks the same. So here's what it looks like. Here's our parameter estimate of alpha, which is fixed and not estimated. And so we get slightly different values for these coefficients, right? So it's not quite the same that we got for just a regular OLS-like model. So then we could go and fit the same set of models, but with OU, right? And so that's what we've done here. So models 5 and 6 are the 2 different ANCOVA models with OU here. So mass and clade, mass plus the interaction between mass and clade, right? So this is the sort of standard set of regressions that we would do normally. And then these are these are just AICs, not AICCs, but they're all going to be pretty similar here. And so again, I think the best model is this one. So an OU model, which is much better than its counterpart Brownian motion model, and that's true for both of these, right? Which says that clade actually does matter in this case. I think it doesn't matter. Like this jump is not so big. This actually jumps us backwards. But if we sort of compare above and below, there actually seems to be some sort of selection going on here. So that's the best model. This has some pretty good support as well, right? So you might think about considering that model too. But if we were just going to report a single model as the best, it's this one. And so that's what that one looks like. It has a slightly higher alpha, so this is 0.035, so a little bit bigger. And then these values are, so now you see in this case, now we actually do get a significant effect of clade. So once we do this transformation, we actually get a significant offset between the two clades. Right. Which again is probably not surprising in this case. So this would sort of be what you would report, right? So you'd report your, the alpha value for the strength of selection, and then basically this would be your ANOVA table for this.
So how many optima did we give it?
This is a single optimum, yeah. So this is not the multiple optimum models of Butler and King. I'm gonna try to work on an example of that for Friday.
It seems it could be easy to get good support for two optima.
Yeah.
In this case.
Yeah. The problem is, so there's sort of two questions though. So that Butler and King, what they were doing was multiple optima for a single trait, not for multiple traits simultaneously, like not for a linear model, right? So I don't know that problem has yet been solved. There's a paper that came out a couple of years ago, which is like the effect of like the still ongoing problem of measuring correlated evolution of multiple characters or something like that, which is like, basically like we still haven't solved this problem yet. So Butler and King, that solves a different problem. But we could take body mass or home range area and look for multiple optima. That's probably what I'll do for Friday, because that's a relatively straightforward thing to do. Take the same data and say, is there a optimal body mass for ungulates and an optimal body mass across the tree?
It makes biological sense,
right.
And they just kind of look like they're very separate. So it seems like an OU model with one optimum for a group that has two very different.
Right.
It seems kind of.
Right, but keep in mind this is sort of optimizing both sets of data at the same time, so it's not, it's not quite, it gets complicated really fast. As soon as the tree gets involved, like we have so many more things now to deal with. Okay, so what was next? Oh yeah, so does that make sense? This is basically the framework is the same kind of framework that we used before, but now we just have this added wrinkle of phylogeny. You could go back and put in a different, you could estimate a Graffin's row transformation, and those might actually fit better. I don't know, right? We don't know. Graffin's row, and I mean that one especially, I feel like is very arbitrary. Like that's no different than just square root or multiply by pi or something like that, right? It's just a very like arbitrary. I feel like at least there's a biological motivation for a lot of these other ones, speciational models or ACDC models or OU models, which I find more appealing than just some arbitrary branch length transformation. And Pgls is largely to me an arbitrary branch length transformation. Probably should actually go back and fit, these AICs should be comparable, so we should be able to go back and fit PGLS with the same data set and get. But we could do Pgls lambda with this, and that'd be fine. I like PGLS, but I don't like that it doesn't do OU models. So anyway, we're stuck with this. So it depends what you want to do. You can decide. One last little note about non-ultrametric trees. if your tree is not ultrametric, you had to do one more step. And this, again, is a GLS only thing. I don't know how Pgls handles this, honestly. I'd have to think about it. I'd probably have to actually try it and make sure that it does it properly. But if you're dealing with GLS, which is usually what I use anyway, you got to do one more thing, which is you have to supply this weights argument, which is partly why I didn't want to talk about weighted regression before, because it gets confounded with weights argument. So we need to pull out the diagonal. So this diag basically just pulls out that diagonal line down the tree, right? And so, again, we know that is just the total height, the total distance from the root to that individual tip. That's what goes on the diagonal. So, bears and whatever are these other things, Panthera, right? We have an ultrametric tree in this case, so all of those are 70, because 70 million years, the theoretical divergence between carnivores and ungulates. I don't know, as it was in 1992. It's 1992, so. So if your tree does not have is not ultrametric, you need to pull that out and include it as this weights argument. And you can see it's like a one-sided formula, tilde W here. You get the same answer. You could, in theory, just do it all the time as a matter of practice, because if these numbers are all the same, you get the same answer. It's like ones in there, right? It's basically like sticking in the identity matrix. But if they're not, then this is what you needed in order to do this correctly. So you could just always do it, and that would always work. Does that make sense? Little wrinkle. All right, that's it. Put your references and things. So questions? So just some sort of housekeeping stuff. We've done a little early. I've talked to, I think, most of you about what you're doing. I just want to know that you've thought about what your project is. And you have interesting stuff. It's good. You're sort of going beyond just, taking some relatively straightforward data set and doing something with it, right? You're actually reinterpreting old data, right? Which is always fun, because, you get to a point you're like, I can't deal with this anymore. You just move on and come back to it later someday, right? So it's not meant to be super involved, right? I mean, it's 5 to 10 slides, which isn't a lot. So, a little bit of introduction, why are you doing this? A little bit about what you did, a little bit about what you think it means, and that's it, right? It's just a chance for you to go a little bit beyond this class and to talk about it in front of a group that's not hostile. All right? At least it shouldn't be hostile. Maybe by the end they will be hostile. I don't know. So that's, do that by Friday. But when it says project due in the last day of class, that just means send me whatever it is that you did, right? Because I probably want to use it as an example in class in the future or something like that. That's all.
Do you mean the PowerPoints or you mean something?
Everything, yeah. Send me everything.
So,
PowerPoints are this Friday or next Friday?
No, this Friday is just
okay.
Let me know what you're going to do.
Okay.
So I know that you've thought about what you're going to do. I think the 14th is when everything is due. Something like that. Is it the 14th? I don't know. I don't have the syllabus. That's going to also be the due date for everything else, right? So the last problem set, which I probably won't. It's not actually going to be due next Tuesday, because it'll include stuff from probably Monday and from Friday and Tuesday. So it'll also be due at that last day, because grades are due. I think that's a Friday. Grades are due, I think, the next Tuesday or something. So I gotta get everything graded and stuff. So everything will be due then. And you all have A's now anyway, so there's no reason why you shouldn't get an A in this class. I fully expect you will. But you do need to do everything. So that won't be due whenever it says that it's due. It'll be due at the end. So everything is due at the end. And so problem set 13 also, I don't. If I get everyone's before then, I'll grade it. But if I don't, I finished 10 now. Finished 10. I have almost everyone's 12. There's a few people that don't have 12 from, so send me those as soon as you can. That's 12 is probably that was pretty hardcore programming stuff. But you think about those as models for things that you could actually do. I mean, those are essentially very generalizable to any sort of an analysis. All these Monte Carlo things typically are kind of one-off, right? You write it very custom for what you're doing, but there are a lot of generalities to them. So Friday we're going to talk about character evolution, and so that's going to be it'll be not just continuous characters, but categorical characters, right? So how do we reconstruct internal nodes? Ancestral state reconstruction will be Friday. We'll do a lot more sort of comparing different models of evolution. We'll do some multiple optima models. We'll do, I don't know, whatever else I think of between now and then. And then the last real meeting, which is next Tuesday, and we'll do sort of co-evolution, which is where the real challenge there is sort of co-evolution of multiple of categorical or discrete characters. Like that's a challenge. So it's kind of like a logistic regression in the sense you can kind of work at it that way. That's one approach to it actually, is logistic regression. Right? Is the presence of something does it correspond with the presence of something else? But there are some other ways that we can get at that. Friday we'll do rates of evolution. How do we detect rate shifts? So is evolution speeding up or slowing down in different parts of the tree? It's kind of cool. A lot of neat new ways to get at things. There are a lot of really, really smart people working on this right now, these general questions. So this is a good time. All right, we good? We're good. All right, see you Friday. I'll see most of you before Friday. The rest of you I'll see Friday.